For those of you who don't know me, I'm David Golden. I've been working on Perl, particularly parts of the tool chain for a long time. I think my most popular module these days is PathTiny. You may have used it. And I'm currently a staff engineer at mongoDB. This is, as you may have seen during our AV sync up, the 9 o'clock slot. It's always kind of an interesting slot. I had the first slot of the day last year. And in the first 15 minutes, the number of people in the room increased by 50% as all those sort of people drifted in. So what I wanted to do, just to kill a couple minutes, but hopefully still add some value to everyone, is I wanted to ask a couple questions of the audience, particularly around what versions of Perl people are using. There's a lot of debates go on in Perl toolchain circles about what versions of Perl do we have to support, and I got into one of these recently at work even. And I find that conferences are a great way to find out what are people actually dealing with in the field. So I'm sort of curious, is anybody in the room using 5.6 in production? Perl 5.6? Excellent, great news. I've never seen anybody still using 5.6, ever, but I keep asking because I keep hearing that there might be these people out there. How many people are using some version of 5.8 in production? Handful of people, excuse me?
But it's the public shaming portion.
No, I don't think it's anybody's choice. We all heard Rick's talk yesterday, 5.14 or die, but it's 5.10 in production, okay, handful of people. How about 5.12, 5.14, okay, a lot of 5.14s, 5.16, a couple, 5.18, 5.20 or later. All right, so that's great news. A lot of people are actually sort of out there with a lot of the recent versions, and I'm glad to see that. Particularly as a toolchain maintainer. Hey, Rick, you just missed it. I asked the room what versions they're using. There are still a couple people on 5.8, 5.10, 5.14, lots of people, 5.18, 5.20, lots of people.
No.
You'll be happy. No 5.6, I asked, no 5.6. And I asked in the Baltimore DC Pro Workshop, no 5.6 there either. So I want to try to prove, as much as you can prove a negative, that 5.6 is actually not in use. And so when somebody says, can you please make this work on 5.6? I can say no. 5.6 should be dead. The tool chain doesn't support it, but there are people who want things to work even back to 5.6. Okay. The other obligatory note I just want to say, of course, I'm from mongoDB, as all startups are. We are hiring. Particularly, we do a lot of work in C++, Go, and Java. I'm on the drivers team where we have to have people who are experts in 10 different languages. So my group actually is looking for polyglot programmers, people who can work across multiple languages. And we also have a number of engineering positions, pre-sales engineering and support engineering, where it doesn't matter what languages you know, you just need to be smart technical people who can help users, customers figure out how to use the database better. If you're all interested, check out the website or find me during the break. I'm happy to talk about it. So now, we've sort of, a few more people like Rick have drifted in, so we'll get back to practical consistency. Understanding consistency is really essential for working with distributed systems. And when I talk about practical, what I mean is not sort of jargon and theory and academia. I've read a lot of academic papers around distributed systems and consistency, and they're a real bear to work through. And the average programmer doesn't need to know all this stuff. And so what I want to do today is give a number of practical questions, ways of thinking about distributed systems that will help people, I think, in their day-to-day lives of programming against such systems. So what is a distributed system? A little recap if people aren't familiar. A distributed system means that we have data processing spread over time and space, which Einstein would sort of say is kind of the same thing. And I'll give an example here of mongoDB. And you'll notice there's a red arrow kind of up in the corner. Everywhere the mongoDB logo shows, I'm giving an example that is mongoDB specific. And so even if I don't call it out on a slide, if you see that little logo, that means this is a mongoDB example of how a distributed system might work. This picture here, we'll see variations of this throughout, so I'll take a moment to sort of explain it. MongoDB is a distributed database. How many people are familiar with MongoDB? All right, fair number, good. So I don't have to do too much recap of MongoDB itself. So MongoDB as a distributed system works by having a client. Here the XKCD style black hat is the client, can read and write to a node which is called a primary. And that node synchronizes data out to other nodes, here B and C, which are called secondaries. And the client can also get a read-only view, can read from secondaries, but can't write to secondaries. So this is a what's called chained replication. So things go to a leader, writes go to a leader, and then replication sort of follows out from the leader to other systems. Here's another system that's a distributed system that a lot of people might be familiar with. How many people have ever heard of memcached? Right. Almost every hand, I think, is up. The people who didn't put their hands up are lying or lazy. So memcached in a database is another form of a distributed system, and here the client reads and writes to both of them, and we'll come back to sort of what the implications of that are later on. Here's another example of a distributed system, etcd. Etcd is a distributed reliable key value store. It's used for like synchronizing configuration across like Docker clusters and things like that. It works where the client can read or write to any node, and the nodes synchronize all of that amongst themselves. And that has certain implications. So there are lots of different ways of organizing a distributed system. And the principles that I'm going to talk about today apply to all of them, and the questions that I'm going to bring up apply to all of them. And even though I give you MongoDB specific examples, the examples are things that you can sort of translate into any system that you're working with. So why do you use distributed systems? Well, the number one reason is scale. Sometimes you just can't fit everything onto one box, or it's too expensive to try to fit everything onto one box, and it's cheaper to spread things across a number of small boxes. Another reason is performance. Lots of things we do in this day and age with big data, we can actually do in parallel. So you can sort of, if you can spread the work across multiple boxes, you can reduce the time you have to wait to get things done. Another reason is redundancy. By having multiple copies of data in multiple systems, then you're sort of protected if a node or a data center or something goes down, because you have replicas that can take over. And we'll focus mostly on this today because it's when you have copies of data in a distributed system that you kind of get into the most trouble. So how do we break distributed systems? One way is by races. Races, there's a great David O did a great talk yesterday about file locking and how you can have races just to try to write to files and what you do about it. And dealing with races is a big part of figuring out how to make distributed systems work well. So races are a problem. The other problem is partitions. When some nodes in a system or some clients can't see all the nodes and the nodes can't see each other, this causes problems for distributed systems. Now, how do we get things like races and partitions? Well, particularly thinking about partitions, a lot of reasons. One is just a crash, right? A server crashes, the program, the database crashes, these things happen. And so a crash can sort of take a node offline. You could have packet loss. Essentially, from an outside observer's perspective, it almost doesn't matter whether the process has crashed, the server has crashed, or a backhoe has cut through the network line. Like if you can't get packets back and forth, essentially that node has gone away. Another interesting situation that people encounter is garbage collection. So garbage collection might pause your application for a while and nothing happens. And in that time when nothing happens, maybe something was expecting something to happen elsewhere in the system and it looks like the node has gone away. And even just processes swapping out. Anything that sort of takes the process offline at a moment when it was needing to do something is a situation that can cause a race or look like a partition. So I'm going to give an example using memcached. This is that I alluded to. So memcached kind of works like this. I'll give kind of a quick recap. This is kind of the Wikipedia level, how memcached works. So let's imagine Black Hat wants to write a value in, for a particular key, the value A, reads it back out of the database to make sure that what that was stored was there, and then stores that value over in memcached. So great, now I wrote it to the database, I pulled it back to make sure that's what was in the database, and now I've saved it off into the cache. Great, now I have and then after that, anytime I read, I'm going to check the cache first, and I'd rather read from the cache than have to read from my database to keep the load off my database, right? This kind of bog, simple, standard memcached. Well, how does that go wrong? Well, I'm going to rewind that to this point. So Black Hat has written the value into the database, has read it back, and right at this point, there's a garbage collection pause. Now here in Perl, we don't worry about garbage collection pauses because we reference count instead of garbage collecting, but you can imagine a process swap or something else that takes the system offline for a moment. And at this point, Black Hat stops. And then White Hat comes along and manages to go through the same process without interruption. Writes B into the database, pulls it back down, stores it up to memcached, and then Black Hat unpause it. Great, I'm done, I can finish doing what I'm doing, and the next thing I have to do is store A into memcached. And now you're really screwed, because now both Black Hat and White Hat are always going to go look at memcached first, and they're always going to look and find the value A, even though B is over in the database. And those of you who have worked with this before think, oh yes, but I have a timeout, or I have a reconciliation process. So yeah, you have a lot of other things you have to do to find that you have an inconsistency and fix it. And this is why a database and memcached is not a good distributed system. At least it's not good from distributed systems theory perspective, but as we all know, lots of people do this, so it's actually probably good enough. There's a lot of cases where that's fine. If you're writing data and it's immutable, you're not going to have this problem because you're not colliding. Like, there's a lot of situations when this is a perfectly acceptable thing to do, but I want you to think about that principle of how the race suddenly winds up with different values of data that you were expecting to have the same. So what makes for a good distributed system? Back in 1999, this guy, Eric Brewer, who's at Berkeley and Google now, I think, came up with something called the CAP theorem. People have heard of the CAP theorem? Fair number of people? Okay, so the CAP theorem, CAP stands for consistency, availability, and partition tolerance, and what Brewer's theorem said was, well, you only get to pick 2 of these. You can only have 2 of these ever at a time. And so if we think about consistency, consistency is the idea that there appears to be a single copy of the data from an outside observer. So even if we have multiple copies of the data spread around, from the client's perspective, looking into the distributed system, it only ever appears that there's one copy of the data, and any modifications appear to happen atomically. There are some weaker models. People might have heard of the term eventual consistency, and there's like strict consistency, and as you get into the literature, there's all different variations of consistency. And it's one of the things that I find sort of problematic because it's actually hard to sort of figure out, well, what all this actually means in practice. So the other factor is availability. So this means that a node failing, either a crash, garbage collection, pause, anything that takes a node offline doesn't prevent the surviving nodes from continuing to operate successfully. And then partition tolerance. Partition tolerance means that the network can lose arbitrarily many messages from any node, and everything else holds true. And as anybody who's ever worked with real systems in the world knows, we can't avoid partitions. So you don't actually get a real choice between all of the combinations Brewer suggests. You really only get CP or AP. You can have a system that is consistent in the face of partitions, or you can have a system which is available in the sense of partitions. So consistent means as long as everything is talking to each other, everything's fine, but if a node goes away, then everything stops and I can't do any more operations because the network is down. An available system would say, well, sure, a node is down, but I can keep operating, and yeah, okay, things aren't going to be consistent, and we'll kind of figure out how to reconcile it later. So that's kind of the choice that he kind of laid out. And then about 5 years ago, this guy, Daniel Abadi, came along and said, you know, this CAP thing is kind of simplistic. It doesn't really capture what we really care about in the real world. And so he said, I'm going to come up with this new thing, and I'm going to call it PAC-ELK. So let's flip around the CAP and let's add some other stuff on it. And PAC-ELK is trying to address the fact that while we think about partitions in an extreme case, most of the time we don't have a partition. So let's think about that. So he says that we really need to think about distributed systems like this. If there's a partition, then we have to pick between availability and consistency. So this is kind of Brewer's theorem here. But otherwise, else, we have to choose between low latency and consistency. And so we're always we have to think about the trade-offs we make under 2 different regimes. One when things are going horribly wrong, and the other when things are operating normally. And if you kind of notice that consistency is in both places, what changes is this question of availability and latency. And so a lot of what I'll be talking about later on are some of these trade-offs between availability and latency in different systems. Personally, I find even that to be still sort of simplistic and kind of ivory tower, because it doesn't really sort of distinguish between the notions of like reads and writes, which might give you different perspectives on this. And I'll give a MongoDB example. So on MongoDB, you can have a replica set and you can have a partition. And on one side of the partition, if you have an odd number of nodes, you have a majority of nodes on one side of the partition. And on the other side of the partition, you'd have a minority of the nodes. And on the majority side, you can still, a client can read and write. And the writing looks consistent. You're not sort of aware that actually there's some minority partition that isn't getting those updates. So to the outside observer, it still looks consistent, which maybe satisfies Brewer's theorem. I'm not so sure. On the minority side, you can't write. You're not available. So to try to preserve some sense of consistency, you can't actually do your writes. You're not available. But you can read stale data. So you are sort of available. So when I look at this, well, it appears consistent even though it's not. You're available. You're not available. You're available, but you're stale. Does that fit into Brewer or Abadi's sort of frame of reference? No. So this is why I want to talk about practical consistency. Leaving all that theory behind, which you will hear thrown around by people who want to have arguments on the internet, I like thinking about what are some practical questions that we should be considering instead. So one of the most important is really around writes. Do I know when a write is committed? And how do I read only committed and or only current data? These are kind of the 2 critical questions we want to think about, writes and reads and what's important. And so thinking about writes now, there's kind of 3 things I want to talk about. So we have, I want you to think about durability, and I'll explain these, convergence and error recovery. And I just want to take a little aside about durability. So when people write databases historically, like things are committed and durable when you've got the operation written to a journal, the journal has been successfully flushed to your hard drive, and your hard drive hasn't lied to you about whether it's actually put it to the medium or not, which is a whole sort of interesting question in itself. In distributed systems land, people think about things being durable or committed when you have a replicated copy in enough places that you'll survive the loss of certain nodes. So we're not terribly worried about whether things are actually fully flushed to disk. We're worried about have things gotten to enough places that nodes can go away and never come back, and the data will still be there. And this is, I think, partly in kind of the DevOps world, there's been this shift in mentality from kind of servers as pets to servers as cattle. If people have heard that expression, servers as the cattle. So the idea is we're not as worried about a server going down and then we're going to bring it back up and nurse it back to life, and so we need to have all the data recovered. It's like if a server goes down, it's dead. We're killing it. We're going to bring up another cloud node and we'll continue from there. And so the notion of whether something is journaled and durable on the disk is less important if you're thinking about just blowing away servers that died and bringing up new ones. So how do we know when writes are durable? Do we even know when writes are durable? And a little bit we can talk about later, like do we even care? So I'll give another MongoDB example here. So in MongoDB, the client writes to the primary node. So we're going to write the value A to the primary, and the idea is that this is going to get replicated off to the other nodes. Once that value has reached a majority of nodes, 2 out of the 3 in this case, then we consider this to be committed. At this point, even if the data doesn't make it to the other node, we think this is sort of committed in the sense that it's not going to go away in the face of a node failure. On the other hand, what if there's a partition separating the primary away from the other nodes? Well, at this point, now, even if you write the value B to the primary, it can't replicate. It can't make it to the other nodes. And so the question is, how do we know that that happened? Do we know that that happened? So MongoDB has a feature called a write concern. And you set it in the sort of connection options of your client like this, assuming that you have used MongoDB up above all this. So W1 says, hey, server, as soon as you got this, like, let me know about it. The other one that you should use, and probably nothing in between, is majority, which says, only tell me a write is committed when it's reached a majority of nodes. And it looks kind of like this. So with W1, you write the value to A, and as soon as A has it committed locally, which does mean journaled and all the rest of it, it says, okay, great. Okay, I'm done. Your write succeeded. Right? So you know that at least your write got to one server. If, on the other hand, you say W majority, you do your write, and now you wait. And while you're waiting, the data starts replicating to other servers. And when it has reached a majority, and the primary finds out that it's reached a majority, it then tells you, okay, so now you have done your write, but now you're blocked waiting. So if you want to fire and forget, because it's data maybe you don't care if it replicates or not, you can use W1. If you really want to know that it became durable, you can use W majority and you can wait. So again, there's always this trade-off between how reliable, durable do you want it to be, and how fast things are going to be. And this is kind of one of the key principles. So that's about durability. So then let's talk about this next question. How will the system converge on recovery? So let's go back to sort of our example where B has been written up to this primary that's partitioned. At a certain point, through heartbeat checks, the old primary will notice that it's partitioned and it will step down. Say, I'm no longer a primary. And a new primary will take over. In this case, it's node C. And node C is the new primary, and that means that node C can take writes. And so a client can write to C. The write can replicate to B, and now you have, again, out of the 3 nodes, a majority have C. So C is now a durable, committed piece of data. Then let's imagine the partition goes away. Somebody found the loose Ethernet cable, plugged it back in, and node A is then visible again. Well, node B then heals itself by looking at what was its last point of common history with the other nodes with the primary, and it throws away all the old data. So it says B, well, that's not in the history, so I got to throw that away. And then it'll replicate C and bring itself back into consistency with the rest of the cluster. So it converges with the other nodes after the partition is healed. So that's the rollback approach to dealing with convergence. Other databases make different choices. Some of them use conflict records as well. They'll just kind of keep the fact that B was written and C was written, and they'll let the users sort it out. Well, here you go. There were 2 writes to this key at different times by different nodes. You figure out, using your own business logic, how you want to resolve that. I forgot to turn off my screensaver thing. All right, are we back? There we go. This is telling me to stop typing and rest my wrists and things, which I don't really have to worry about here. My thumb, maybe. Other types of databases use something, and this is a little jargony, called conflict-free replicated data types. And the idea is these are data types that fundamentally can merge themselves together following consistent predictable rules when you have different values written to different parts of the system. And so an example of that would be like add to set. So if what you had was a set or a bag, and you were adding B to the bag, and some other node had added C to the bag, then when you put them back together, you can say, well, just merge it all together, and the bag now holds B and C. And so those are sort of data structures that have rules for combination. Different systems have different approaches to this. And I guess the point to you is, when you're using a distributed system, you need to know what the convergence rules are. Another thing to think about is, what do we do with a write error? So we go back to this sort of situation where we're doing a W majority write up to the primary, so we're saying, I only want to hear back if this has reached a majority of the other nodes. Well, one situation is you could just block forever on that, but typically what happens is you have some sort of a timeout. And when the timeout happens, you get a message back saying, error, couldn't do it in the time you specified. And then you have a situation where you know that your write has failed, but now what do? Do you retry it? Do you ignore it? And unfortunately, like, that's kind of, it kind of depends on what the data is and what your use case is. If this is like sensor data or log data, maybe you don't care and you just throw it away and wait till some writes succeed. On the other hand, maybe it's something that really needs to live there. So unfortunately, the answer to this is it's application specific. There isn't even a mongoDB way of doing this. It's simply like you get the message that it failed, and then you have to apply your own business logic for your application to figure out, well, what do I do next? So that's all about sort of writes. Let's think a little bit now about reads. And while you think about reads, I'm going to refresh myself, which I can't keep on the podium because it's tipped, and I would worry that we'll have a fatal accident. All right, so as we think about reads, three things again to think about: recency, durability, and latency. So recency is kind of how old is the data when you read it, staleness. Durability we talked about. Latency is how long does it take to get an answer. And so here are some of the questions we want to think about are, there we go. Do we care if we read the latest write? Like, do we have to get the absolute latest information, or can we get some data that's lagging a little bit? And that's kind of a stale read. Or do we care if the data we read rolls back? In sort of traditional database terms, this would be like a dirty read. So some data was written, maybe it's not made it all the way out, but maybe we want to read it. Do we care? And so this leads to some trade-offs. So the first trade-off to think about is recency for durability. Do we want to read before we've fully replicated the data to the point where it's durable? So that looks kind of like this. So again, we'll have black hat writing B to the primary that's been partitioned. The write can't replicate, but maybe white hat comes along and wants to read from the primary and reads down that value B. So this is a dirty read. So it's read data that we know from if other writes go to the primary. B could get rolled back. B could get thrown away, but white hat has read it. Now, this would only happen in a narrow window because that primary will notice that it has been partitioned and will step down at some point. But if we have a race and white hat sneaks in and tries to write just before the primary notices it stepped down, it can say, yeah, I'm reading from the primary. I think this is the latest data, but actually it's going to be thrown away. Maybe that's okay. Different applications might have different views on this, whether reading that kind of data is okay. You know, I think about all the times I'm on like some social network, Twitter, Facebook, whatever, and you hit refresh and like some story or thing that was there is now gone. Right now, maybe that was an algorithmic change that like decided to like hide some story and show me some other story, or maybe the data went away. As a user, I don't know. And if my users have been trained to not really sort of care about things appearing and disappearing, then maybe giving them a very fast answer is actually more important than giving them an answer that won't go away. Because if it goes away, they'll just be like, oh, whatever. I guess that story got deprioritized off my feed or whatever. So applications can make these sorts of trade-offs. In MongoDB, you make these kind of trade-offs with another thing that was introduced in 3.2 called a read concern. And so we have these read concern levels, and apologies for why this is long instead of being R like the other one was W. Never mind, catch me at the break. But the idea of read concern level local is you're asking the server, just tell me what you've got locally. I don't really care about replication. Just give me whatever you've got. And majority says, I only want to hear back from you. Only give me data that has made it to a majority of nodes. I want to make sure that things I'm reading have actually been committed. And so it works kind of like this, where let's assume that B has been written and is in the process of replicating, and white hat does a read concern level majority read. At this point, the system sort of ignores the fact that B is there, looks back to the last thing that actually made it out to all the nodes, which is A, and hands that back to white hat. And you can kind of see from this that that means that even in this situation without a partition, white hat is reading stale data, right? It's like here's sort of a, it's stale in the sense that it's not the latest write, it is the latest committed value, but it is essentially something that's lagging everything else. So it's saying, well, I really want to have stuff that won't roll back, and I'm willing to accept slightly old data in order to get that. So another trade-off we can make, and it's worth thinking about, is trading off recency for latency. Maybe I don't want the newest data because I want answers faster. And so here when we talk about latency, usually what people are thinking about is the round trip time between the client and wherever the data lives in the system. So now I'm going to enhance the previous example by saying, let's imagine that we have two different data centers. Green would be like US West Amazon, blue would be US East Amazon. We have the primary and a secondary in the west, and we have a secondary in the east. Well, white hat is also in the east. And white hat has a 100 millisecond round trip time to the west, or a 10 millisecond round trip time within its own data center. Maybe white hat actually wants results fast. So we have something in mongoDB called a read preference, which essentially says, do I want to read from the primary wherever it is, which is the default? Like the primary could be in Tokyo, and here we are in Orlando, and we're going to be reading from Tokyo and taking all that lag because that's where we're going to read from by default as the primary. But you can also say I want to read from the nearest node. Find the nearest node in network round trip time terms. It may not be the physically nearest node, but it's nearest in round trip time terms. Or within the sort of a window, but that's another sort of detail that we don't need to get into. But the idea is I want to read from something close to me. And when you decide to read from something close, you get situations like this. Black hat writes B, B starts replicating. It makes it very quickly to node B in the US West, but it's taking a while before it makes it all the way over to node C. And in that time, white hat can come along and read A from the node that's in the west before B gets there. So it's older data, but it takes 10 milliseconds to get it instead of 100 milliseconds to get it. So this is another sort of trade-off that applications can make. Different applications, again, may want to make different choices. And whether it's MongoDB or any other system, you should be thinking about where are these trade-offs in the system that I'm using and what do I actually want for the application that I have. Now, there's another gotcha that I want to talk about. And we talk about races. There are races all over distributed system. And one of the most critical and hard to deal with is a partition detection race. So we talked about like data races of different clients trying to write. Well, one of the other issues is just figuring out when does a partition happen? And all the different nodes and all the different clients find out about partitions happening at different times. And so depending on when exactly people detect the partition, you get more kinds of races. So again, in MongoDB land, you could have a situation we talked about before where partition happens between node A and the rest. And for a brief moment of time, node A hasn't stepped down. I'm going to call node A a lame duck primary. And node B has taken over as the new primary and has just been elected. Black hat doesn't know about the new primary, but white hat does. And so you get the situation where white hat is very happy to write to the new primary and write to the secondary. Black hat is reading some data from the old lame duck primary before it steps down. At this point, black hat thinks, even if this is using I want majority read concern, I want all this sort of things. Says I'm reading from the primary. I think I'm getting the latest copy of the data. I know is committed and all the rest of that. But B is actually the latest data that's committed because it's made it to two nodes. But black hat thinks that A is because it's reading from the stale primary. So, well, what if that's not okay? And when might that not be okay? And what is there a question? Money. Money. Passwords was the other one I thought about, right? So like, I change my password, and some other node is handling the login from Black Hat Hacker in Asia, and I really want that node to be making sure that it's got my latest password and not the password that existed a millisecond ago that maybe is letting white hat log in. So I think like passwords are one of those things where you kind of really do want to have the absolute latest value in the system. And so there's only one option for this, and I call it the nuclear option. And I put this out there because it is a very severe way to do it. And essentially, you have to do something in many systems called a quorum read, which is kind of the academic jargon. But the idea is you have to go out to enough of the nodes to make sure that you actually have the latest value across enough of the nodes to know that that's actually the latest value and not a phantom latest value. Or you have to ask a node to do it on your behalf. So it's sort of, and it's very, very expensive to go out to lots of places and check instead of going to one place. One way to do this, and kind of in the MongoDB world, you have to sort of read via writing. And so MongoDB offers a feature called find and update, which is kind of like a compare and swap. You can say, find a document that matches a certain criteria and modify it in a certain way. And you can either get back the old unmodified one or the new modified one, but essentially it's kind of like a compare and swap operation. And if you do this with W majority, you won't get an answer back until that's made it to a majority of the nodes. And at that point, you know that whatever you're getting back was written to a primary node that could see the majority. And what your actual modification is below, find one and update, you kind of increment a dummy field. Here's some dummy field that's just a counter, and I'm just going to increment this every time I read it. And essentially, you've turned a read into a write. And as everybody knows from any other database work they've done, writes are much more expensive than reads. But when you absolutely need the nuclear option, you can do it this way. It is possible, actually, that in MongoDB 3.4 coming out this fall, there'll actually be a new read concern level, which will kind of do this automatically without needing to go through the find and update and the dummy increment process. But it's still going to basically pay the cost of a write in order to do a read. So some of the takeaways from this. There we go. Click or fail. Cap is simplistic. You'll hear a lot of debates online. If you go and read what people have to say online about distributed systems, there's a lot of like cap this, cap that. This system is CA or CP. This system is AP. Blah blah blah. I think that's very simplistic. I think you should think it's simplistic, and I think you should realize that reality is very complex. Very critically, people's needs are application specific. Like there is no one database or one system that's right for every application. There's no one way to do your reads or do your writes that's right for every application. If you are consuming logs, if you lose a log line or two, maybe you don't care. But maybe you need to actually just make sure you can keep up with the throughput of the log data coming through or sensor data. Other situations, money, passwords, maybe you really do care that things actually get changed when you think they're changed. You need to know. So you need to be able to know that the system you use can let you make those trade-offs that you need for your application. When writing, remember, think about durability. How do you know when something is durable? Know how something is converging when a system recovers from a partition. And how do you find about errors and how do you recover from them? When you're reading, think about the trade-offs between recency and durability. Do you want recent data that might go away? Recency versus latency. Do you want recent data that gets the answer fast instead of having to wait around? And think about the nuclear option. When do you need the nuclear option? Be very clear that you're paying a heavy cost, so use it only when you need it. That's sort of all the meat of practical consistency. I hope that it gives you a better sense of what the issues are and what you should be looking for in any distributed system, MongoDB or otherwise. Before I wrap up, I have a favor I want to ask of everybody. This is sort of somewhat personal. So I, among other things, I'm the primary maintainer of the mongoDB Perl module on CPAN. And and I work in this group of driver engineers that maintain the drivers for all the 10 different languages. And they constantly have these questions from management about is this stuff getting used? And some of the newer package management systems give download statistics of how many things have been downloaded from Python's repository, et cetera. Well, CPAN, being a wonderfully distributed system of its own, doesn't give you anything like that. What's actually interesting is that this ++ number on MetaCPAN has actually been a signal that management has looked at and said, oh, that's great that there's a lot of people actually go out and clicking ++. So if you use MongoDB, if you have any positive feelings about MongoDB whatsoever, if you liked my talk, please consider going out and giving a ++ on MetaCPAN and drive this number up so I can convince my bosses that the Perl community is actually interested in MongoDB. If you haven't used MongoDB, I'll take questions in a second. If you haven't used MongoDB, there is, if you download the MongoDB driver, there's MongoDB : tutorial, which kind of walks you through how to do some basic stuff, and university.mongodb.com has a number of free courses. There isn't a Perl-specific one yet because I'm busy actually doing the work on the Perl driver, but there's a Python course, and you can almost translate the examples directly over for use with the Perl driver. It's all free, and I encourage people to check it out. Now I'll take questions. Steve, you had a hand up that I saw.
How many pluses do you really need to get?
Modulicious is #1, and they're up or around 280 maybe, last I checked. Somebody with a computer on the internet can tell you what the high numbers are. I think MongoDB is currently 44 out of 100, yeah. I would like it to not look like it has been totally engineered. So if it suddenly gets to 400, that might be a problem. If it goes from where it is up by 10 or 12, that'd be great.
So it needs eventual high number over
Eventual.
Yeah, exactly. Eventually, it needs to look like it was consistently clicked by lots of people.
you need to spike after your top.
Yeah, I did it last year, and I tweet about it periodically, and I get a little tick up and a little kick up. You know, and it's weird. Management looks for signals, right? And when you, in the absence of anything else, I can tell them. I can say, well, hey, we're number 44 out of 100 on the CPAN Meta CPAN most clicked list. Does that say that the community really loves it, or I'm just a good salesperson of getting people to click it? I don't know, but at the very least, it will help me out. And MongoDB has been a big supporter of Perl. A lot of the sort of new NoSQL databases, they're happy to put out drivers for Ruby and Python and Java. Very, very few companies actually internally develop and support a Perl driver. MongoDB does. I'm very excited to be the person leading that effort. So I definitely would love for the community to show MongoDB that the support, so that MongoDB feels like it's a worthwhile investment to continue developing Perl. When Larry gave his Craigslist talk, was it last April? Something like that, he gave his talk saying it's coming out, which was really the announcement that it was coming out that Christmas. Yeah, my team lead came in and said, "Do we need to start developing a Perl 6 driver?" I said, I think it's okay. It's not out yet. There is a Perl 6 MongoDB driver that was a port of an older version of the Perl 5 MongoDB driver. I haven't really sort of looked at it, but I'm in contact with the maintainer, and we talk about issues, and I kind of try to point them to things that might be helpful as versions change. So I kind of keep tabs on it, but I don't have the bandwidth to get more directly involved. Other questions? MongoDB or distributed systems related? No? All right, thank you very much. Appreciate your attention.